Hey y'all, I'm Gracie and this is Lab 5, Magnetic Braking with Faraday. Introduction. Using a bar magnet and an aluminum foil tube, Faraday's law can be observed by dropping the bar magnet down the aluminum foil tube. This experiment is then modeled in VPython. Some physics principles used are Faraday's law, Lenz's law, Newton's third law, and Newton's second law. Some results from this lab are the average time for the magnet to fall is around 1.4 seconds, and the VPython simulation magnet fall time is 1.191 seconds. The experiment. This is where we dropped the magnet down the aluminum foil tube, as you can see in this GIF. The time to get through the tube for 5 different trials are shown here, and the average time is 1.4 seconds. Some measurements of the tube. The length is 0.32 meters, the width of the foil is 0.013 meters, the radius of the inner tube is 0.015 meters, and the weight of the tube is 0.064 kilograms, and mu from Lab 3 is 6.6134. The coding. Here, this is what the tube actually looks like when it's all coded out, and this is the velocity versus time graph. Now into the actual coding of the lab. Step 1 is just entering in some properties of the magnet. Step 2 is to create a function to calculate the magnetic field of the bar magnet. This is done using this equation, which is translated into this function. Step 3 is to create a function to calculate the magnetic flux, and that is done using this equation and translating that into this code. Step 4 is to calculate the current in the ring. We know EMF is equal to the magnitude of the change in magnetic flux, and therefore current is equal to the EMF divided by the resistance, which is translated into the code. Steps 5 and 6 are to calculate the magnetic field at each ring. That is done using this equation, which is translated over here. Just as a side note, sine theta is equal to this. Next, step 7 is to calculate the net force, which is just the magnetic force and the gravitational force. And finally, step 8 is to update the magnet's velocity and position using Newton's second law, which is shown right here. Coding and direction of current. The counterclockwise current is represented in blue. This occurs at the top of the magnet, and this happens because the magnetic field is pointed upwards and the magnetic field is decreasing because it is falling through the tube. Lenz's law states that this induced current will be in the counterclockwise direction. At the bottom of the tube, the current flows clockwise, represented in red. Because the magnetic field is still pointed up, but the magnetic field actually increases at the bottom of the magnet. So by Lenz's law again, the induced current would be in the clockwise direction. Now, if the magnet were actually flipped, the magnetic field would still be decreasing as it's still falling through a tube, but the magnetic field of the magnet would be in the opposite direction. It would now be pointed downwards, and the induced current would now be in the counterclockwise direction. Once again, this is Lenz's law. Coding the fall time and the shape of the graph. The overall time the simulation found for the magnet to fall is 1.191 seconds, and the real-life experiment was 1.4 seconds. The computational simulation could be made more accurate by adding more rings to represent the aluminum tube better, as well as accounting for things like air resistance. Next, the shape of the velocity versus time plot indicates that the forces acting on the bar magnet are slowing the magnet down and acting oppositely to gravitational force. Conclusion. What if the resistivity of the conductor were reduced as close as possible to 0, and how would the dynamics of the falling magnet change? The current would be infinite, thus making the induced magnetic field infinite, that points in the positive y direction. This creates a magnetic force on the magnet in the same direction. The magnet would begin to fall, but then ultimately float due to the strong magnetic force from the induced magnetic field. Finally, what if holes or slots were cut into the tube, and how would this affect the ring currents in your model? If holes were cut into the tube, the magnet would fall faster through the tube. At the locations of the hole, there is no current induced because the tube does not fully encompass the changing magnetic field, and therefore no current can be induced. Since there is missing spots of induced current, the magnetic force that would be induced at these spots also does not occur, so the overall net force is less, allowing the magnet to fall faster. Thanks for watching.